So we can ask the question, when we're juggling the 3, 3, 3, 3, and we want to change to 5, 1, 5, 1, what goes in here, right? So, very similar to this argument, what I showed you on the board, we can't just change directly, right? If we just go straight from 3, 3, 3, 3 to 5, 1, 5, 1, see in this case, we've got a 3 here and a 1 there. So we can't do that because of the distance rule, okay? Because 3 minus 1 is 2, their difference is 2, and they are a distance 2 apart. So that's not going to work. So the distance rule is not satisfied in this case, right? So this is just explaining that. So we know we're not going to be able to juggle that, right? Now, but I just did it, right? I just did it. I was just juggling. Here's a 3, and here's the 5, 1. So what happened in that transition? Right? What happened in that transition? Have another look. Yeah, there's a 2. Exactly. There's a 2. So this is precisely what I did. We need to modify the pattern around this transition. Okay, and so we've got 3, 3, 3, 3, and I did a 5, and there's a 2 in there somewhere. And that saves the day. That makes everything okay. All right, because that now the distance rule is not broken, all right? The distance rule is okay, and then I can work out the transitions. Unfortunately, the permutation test doesn't really have a context here, right? Because we're talking about transitions now we're actually starting to ask the questions, how do we start, or how do we go from one state to another, all right? A little bit reminiscent of energy levels and anyway, and excited states and so on, but it's another thing. So going back the other way is just as easy as I've demonstrated here. Okay, so we can throw a 2 in there. So if I start juggling 3, there's the 2, and I'm doing 5, 1. Now I just hold on for one beat, or I throw a 2 in there, going from a 5, 1 to a 3. Yeah? Okay, so this pattern I have a little bit of trouble with. I have a little bit of trouble juggling that pattern, but I can demonstrate by using Joe. Oh, he just did a transition. Oh. So what are we looking at here? We're looking at a 5. I'll just write this up. Hang on, I just go back and have a look. So a 5 to a 5, 3, 1 to a 5, 1. Sorry, a 5? I mean a 3, I think. Did I write 5 up there? Oh no, 3, okay. So it's a little bit hard to spot these different patterns. But for instance, now I think that's a 3. And now he changes to the 5, 3, 1. Now to the 5, 1. And now back to the 3. Yeah? Okay, and you can see it was all a perfectly smooth transition. All right, so he's only using 3 balls for each pattern, and the transition makes, or by adapting the patterns from here to here and from here to here, it makes the transitions possible. And so that means now, as an entertaining juggler, we can sit here and do lots of different patterns and entertain the audience that way, right? So we can actually use transitions to help us that way. That's, of course, if we're interested in entertaining. Now, one last interesting thing, I guess, given that we've seen transitions, okay, between different patterns of finite length, well, here I've got the title Juggling Irrational Numbers. I couldn't exactly work out what to call that. It's not technically correct to say juggling irrational numbers. I guess what I mean is a decimal expansion of irrational numbers. So is it possible, this is the main question here, is it possible to juggle a pattern that never repeats? Well, except for the fact that in principle we would be juggling forever. But apart from that, well, now that I've shown you transitions, theoretically, yes, it is possible. It is possible to juggle a pattern that never repeats. So one way of constructing such a pattern is to just start by transitions through all the patterns of length 1. So say we had 3 balls, right? Turns out there's only ever one pattern of length 1. So perhaps that's what I've said here is trivial just at the start. So we could start with, say, the pattern 3, and then we transition to through all the possible patterns of length 2. Okay, so we've got 2, 4, we've got 5, 1. I don't know, are there any others? 0, 6. Does that work? 0, 6, maybe. Okay, and then work out transitions to all the patterns, that is every possible pattern of length 3, and so on. Now I showed you much earlier that we can use an algorithm to construct all possible patterns, all right? And it's actually true that there are infinitely many patterns, right? Given only the number of balls, there are infinitely many patterns, right? Maybe there are only finitely many patterns of length 3 and of length 4 and so on, but I can keep going up to any length at all and there are still finitely many patterns. So as long as I've got transitions, then it is possible. Okay, so essentially there are 3 parameters, if you like, that are used to distinguish juggling patterns. There's the number of balls that are used, there's the period of the sequence, or in other words, the length of the string, and there's also the maximum throw height. Okay, well, it turns out if we only fix the number of balls and we leave the other 2, so we only say set the number of balls equal to 3, and we allow these other 2 parameters to be completely free, then we have infinitely many sequences or infinitely many patterns. And in this way, we can use transitions to link them together and hence generate a string of integers that never repeats. That is also a possible pattern to be juggled. All right, so just for a bit of fun, I mean, here's an example that might get you started. Get you started, well, yeah, maybe. We start with 5, 1, 5, 1, 5, 1. We throw in a 2 there to transition to a string of 3s, right? Turns out we can transition straight to 4, 2, 4, 2. There's no problem there at all. Yeah. And then there's another transition in here, transitioning from a 4, 2, 4, 2 to a 2, 3, 4, 2, 3, 4. All of these are 3-ball patterns. Okay. Again, this is one of those patterns 4, 4, 1, 3. 4, 4, 1, 3. Ah, yeah, that was this one, 4, 4, 1, 3. Okay, if you remember, 4, 4, 1, 3, and so on. Okay, so does everyone get the idea?
How shall we find transition? Is the transition can be constructed algorithmically?
That's a good question. I'm not sure of the answer there. But one thing I'm quite confident, and I don't have a proof of this, but I'm quite confident that there always exists a transition between 2 patterns. I'm not exactly sure how I could prove that, but I have a suspicion it might be possible to have a look at the permutation test on two of these strings linked together through a transition and to provide a constructive proof. I imagine that's how it might proceed, but I haven't done that, and so I'm not aware of a result like that. So that's a really good question. The other thing is, as long as there's a pattern that can be juggled, I know it's always possible to do it physically, which means there must exist a transition.